Here we are again. Let's talk about crown ethers. Crown ethers are a specialized version of ether molecules. In particular, they correspond to the cyclic components that contain multiple ether units within it. And as you can see in these pictures, you can have 4 oxygens present, 5, 6, and the size of the overall chain changes accordingly. In every single chain, you do notice that you have 2 carbons for every 1 oxygen. So if you have 2 carbons, here's an oxygen, 2 carbons, another oxygen, 2 carbons, another oxygen, 2 carbons, another oxygen. So in total, you have twice as many carbons as you do have oxygens, or if you want to look at it this way, you have 3 times the number of non-hydrogen atoms. And so when you look at it this way, the total number, of oxygens, times 3 will tell you how many non-hydrogen atoms you have present in your molecule. And as such, we refer to them by a rather simplistic denomination. The molecule here on the left side is 12 crown 4. 4 because you have 4 oxygens in it. And if you multiply 4 times 3, you get 12. So that's where the name comes from, 12 crown 4. Over here you have 5 oxygens, so this is a crown 5. But 5 times 3 is 15, so this is 15 crown 5. And by the same logic, 6 oxygens multiplied by 3 give you 18. Therefore, this is known as 18 crown 6. And the reason why we call them crown ethers is because the way they arrange themselves is such that the oxygens kind of point in the same direction. And it kind of looks like this tippy points of the crown that you see here on the right side. So, what ultimately this serves is to have a source of electrons that can be donated to various things like metals. And this particular design, which was perfected by the three fella individuals right here, Cram, Len, and Peterson. These individuals won the Nobel Prize for creating these molecules. And you might say, well, okay, I mean, they look kind of cute, structurally speaking, but, what's the big deal? Like, why was this, worthy of a Nobel Prize? Well, I'm about to show you why. In order to understand really the reason why these molecules are important, you have to pay attention to how they get made in the first place. And if you do mix, for instance, ethylene glycol with a strong base like lithium hydroxide, what happens is that the ethylene glycols coordinate to the lithium via those coordinated covalent bonds, leaving the hydroxide as a naked anion, which ultimately removes a proton out of one of the ethylene glycols and creates this alkoxide functionality. And by the way, the formation of these complexes is also aided by what we call the chelate effect, which is simply the fact that the same molecule has 2 or more anchor points that can bind to the same metal. So the fact that you're binding this alcohol to a metal means that now you're going to have extra positive charge being provided onto that hydrogen, making the pKa of that OH bond lower than it normally would be. So you can actually now deprotonate with even hydroxide. Um, Now, if you add to this mixture dichloroethane, so 1,2 dichloroethane, what you can see now is that you're kind of pre-organizing this entire complex to do the following. Pretty much this oxygen right here, this alkoxy oxygen, can attack via SN2 the electrophilic carbon over here, kicking off a chloride. And now what happens is that you start kind of creating this backbone, right? And so bring in your lithium hydroxide, now you can deprotonate another oxygen right here, and then that creates a new alkoxide that attacks the other end of that dichloroethane molecule that we had to start with. And so you can see that in this process you start kind of building up that molecule, and it's all pre-organized because you already had the ethylene glycols bound to the metal center, so it works out very neatly that you can form these structures. Now the size of lithium, the ionic radius to be more specific, is 0.9 angstroms. So it's on the small side compared to the other alkali metals. And so you get to make more efficiently this tetrahedral looking crown ether that is bound to the lithium ion. And of course, lithium ion still has the positive charge, so you will have the chloride in there to cancel out the charge, but it's not bound to the lithium. It's basically pretty much separate and taken further away from the lithium that you will have in your normal lithium chloride salt. If you move from lithium to sodium, well, the ionic radius now increases, and what this means is that you have more space available around the metal to accommodate more oxygens, and as such, with sodium, you can actually get up to 5 different oxygens surrounding the sodium, and then this gets you to the 15 crown 5 ether, which now it's coordinated to sodium plus. So once again, the chloride is on the outside. Change that to potassium, which is even bigger than sodium, and now you can accommodate more oxygens, and you can get to the 18 crown 6 structure. And it's all due to this preorganization that has to happen as the ethylene glycols bind to the metal center. So the best way now to utilize this, and this is the reason why the Nobel Prize was assigned to these 3 individuals for coming up with the synthesis of these materials, is that because they are made to bind to cations, and they surround the cation in such a great way that they basically aid in the synthesis process. Specifically, if you're trying to bring, let's say you're trying to do a halide exchange via an SN2 reaction, well, chances are your halogen it's going to be part of a salt, like in this case potassium iodide, which really is not all that soluble in organic solvents. This will dissolve pretty well in water, right? But water is not going to be miscible with most organic solvents. So you might have 2 layers, as you can see right here. All right, so what happens is that if you introduce the crown ether into the mixture, well, the crown ether is mostly hydrophobic in essence because you have a lot of hydrocarbon present on it. But this has enough oxygens that can definitely interact to some degree with the aqueous layer. And here at the boundary, your solvated potassium ion can come in contact with the crown ether. And the moment that happens, the crown ether now sequesters that potassium ion. And now that the water molecules have been displaced entirely, and and the potassium is surrounded by the crown ether that is rather hydrophobic, now you can actually bring it into the organic layer. But you don't just bring the potassium ion, you also bring the iodide because the charges have to be cancelled out. So you bring the 2 of them together to make this happen. And now when this takes place, you now have iodide present in your organic solvent to carry out your SN2 reaction. So here is the exchange. Now we have the iodide and we have formed the chloride. And so what happens now is that you bring that molecule over to the surface that separates the organic and aqueous layer, and you basically exchange that chloride for a new iodide. And then you repeat the process by bringing your crown ether iodide back into the organic layer, and you carry out your SN2 reaction. And then so this is the way in which this aids synthesis, and it's a very clever way because now you can do biphasic reactions, which may have incompatible solubility for some of your reagents, but now you allow the compatibility to take place by introducing the crown ether that has kind of this dual effect. It serves as the chaperone, if you will, for the iodide. And so this definitely was a great achievement in synthetic chemistry, and the use of just relatively simple organic chemistry to make some big changes, some big leaps in the world of synthesis. So this is definitely a prize well deserved. And to each one of these individuals, we should take our hats off, and definitely, say good job to all of you for making this happen. Okay, so this concludes the ether chapter. I hope you enjoyed it. It's not as fully loaded with mechanisms as the previous or even the next set of lectures that we're going to see, but it is a cute, interesting chapter. So with that being said, I will see you in the next lecture series. Bye bye.